Hello, dear students. Very good morning to all of you. We are here for the guest lecture in the NMR spectroscopy. So I'm very much happy to introduce to you to Dr. PKP Gayatri Chopra ma'am. She is from Datta Meghe Institute of Research, Savangi Meghe, Wardha. And she's very good and close friend of mine. And indeed, I'm very much happy that she has accepted my invitation to be the guest lecturer for today's guest lecture. Right, ma'am. Without wasting much of your time, I just wanted to hand over the studio to you. Over to you, ma'am.
Thank you so much, ma'am. Thank you for the introduction, and thank you for giving me the opportunity to deliver this lecture for your students. So, good morning, students. I'm Dr. Gayatri Chopra from Faculty of Engineering and Technology, Savangi Meghe Wardha, and I belong to the university, deemed university, that is Datta Meghe Institute of Higher Education and Research. So today with you, I'll be talking regarding this few basic principles of NMR, that is nuclear magnetic resonance. So before we start with, I'll just give you, ma'am, please next slide. We'll see what are the contents that we are going to see today in this particular presentation. So the contents go in this fashion that we'll see a small introduction on the NMR spectroscopy, its instrumentation and chemical shift, scales used for NMR spectrum, spin-spin couplings, solvents used in NMR spectroscopy, the standard used in NMR spectroscopy, and a few simple molecules, the NMR spectra of a few simple molecules that you must have heard of, like ethanol and all. These will be the examples taken in this last content of this particular presentation. Next. So before we start with the NMR spectroscopy, we should first understand what is spectroscopy. It is nothing but the interaction of light with the molecule. So whenever we talk about light, we come to a term called as electromagnetic spectrum. So electromagnetic spectrum is nothing but the arrangement of the electromagnetic radiations in the order of their increasing wavelength and decreasing frequencies, you can say. So that the spectrum that you can see on the screen is a spectrum which is an electromagnetic spectrum which is being shown in the order in which the wavelength is increasing and there is decrease in the frequency, or you can say that decrease in the energy. So this wavelength, this spectrum of electromagnetic radiation, it interacts with the molecules in different ways. See, there is a small portion of visible radiations shown. So this is the very small portion of the electromagnetic spectrum, which we can, what we can say is, which we are very much accustomed to. And the other radiations that we are not able to, we are not very much in contact with all these radiations, but then these also help us in deducing the structure of various molecules in chemistry. So we in NMR deal with the radio waves. So NMR spectroscopy basically deals with the interaction of radio waves with the molecules. Not only, I won't say molecules, it deals with the interaction of radio waves with the nucleus of the molecule. Ma'am, next, please. So this is your nuclear magnetic spectroscopy. So we go from here, that is the spectra which is shown, next, to here. That means how we can, ma'am, next slide, how we can deduce the structure of the molecule from those spectra, the spectra which was shown. So in NMR, we'll be studying from here to here. That means from these spectra, how can you deduce the structure of a molecule? Next. So the very first Nobel Prize regarding the NMR spectrum was given in physics in 1952 to two very renowned scientists who had worked for the development of new methodology of the nuclear magnetic precision measurements and discoveries in the connection therewith. They worked separately, Felix Bloch and Edward Purcell. So we'll now see what basically is, ma'am, next, what basically is the nuclear magnetic resonance. So if we see any molecule, it has, if we come down to the atomic level, if we see any atom, we'll see that atom contains a nucleus. A nucleus has its own spin. It rotates and revolves. So during this rotation, it has both its it can have its magnetic field induced because of the rotation it is doing. So every nucleus has its magnetic component. So basically, nuclear magnetic resonance, it involves the interaction of the oscillating magnetic field of the electromagnetic radiations and the magnetic energy of the nuclei. It could be either a hydrogen nuclei or any other nuclei when they are placed in an external static magnetic field. That means NMR is nothing but the interaction between the magnetic component of the electromagnetic radiations and the magnetic component of the nucleus of an atom. And when these two are placed in an external magnetic field. Ma'am, next. So this slide gives you an indication, or you can say this gives you the behavior of some common nuclei which are magnetic in nature and which can show you the NMR spectra, or we can say which are NMR active. See, here it is the magnetic in the in the heading in which I've written magnetic, all the nuclei having odd number of protons or the odd number of neutrons, they are NMR active because they have their own magnetic moment or magnetic component. Whereas the nuclei with even number of either both protons or neutrons, they are non-magnetic in nature, and so they are NMR inactive in nature. So here are few examples of the nuclei which are NMR active. H1 is a very common nuclei we studied. C13 is again a very important tool, C13 NMR. Then you have N14, F19, P31. These are the nuclei. H2 also is a nuclei which is having its magnetic component, and so it is NMR active. Whereas C12, O16, S32, these are non NMR active nuclei. That means they do not give the NMR spectrum. And please next. Now here, see, as I already told, the nucleus has its own spin. So all the nuclei in the very first, you can say there is written no field. So in this particular area, there is no application of external magnetic field, the magnetic moment of the nuclei, it is directed randomly. There is no particular direction in which it is oriented. Now, as soon as we apply an external magnetic field, so all the atomic nuclei, what happens is they align either parallel to the applied magnetic field, that means they have lower energy, or they are anti-parallel or in opposite direction of the applied magnetic field. That means they are having a higher energy. See, here we have shown few nuclei who are in parallel with the H0, that is the applied magnetic field. And few of them, they are against, or you can say anti-parallel to the applied magnetic field. So these are the two different orientations that your atomic nuclei can take in presence of an applied magnetic field. Next. So here again, we are applying the magnetic field so that the nuclei, they are oriented either parallel or in the anti-parallel direction. Next. So here, see, very first is the ground state. In the ground state, you can say 6 nuclei we are showing. Okay? Now, in the ground, we say that any nucleus is resonating by application of electromagnetic radiation, or you can say radio waves in presence of H0 only when it absorbs the radiation. Here it is shown with a yellow arrow, that is H nu, and it goes to the higher energy state with a flip in its spin. See the blue nucleus that was in the ground state, it is in the direction of the magnetic field, applied magnetic field in the ground state. When it has absorbed energy and it goes to the higher energy state, it has a flip in its spin. If this happens, only then we can say that our nucleus or the atomic nucleus is in resonance with the applied magnetic field. Ma'am, next. See here, as I've already said, the magnetic nuclei is said to be in resonance with the external magnetic field if it absorbs energy and it goes to a higher energy level. It not just goes, but it goes with a spin flip. So if it goes with a spin flip, it is into the higher energy level. Otherwise, it is, if it is in the it remains parallel, it is in the it is in the lower energy state. Now here we can see earlier there were 6 nuclei in the lower energy state or the ground state. One of it flipped, went to the higher energy state. So population in the lower energy state has reduced. Here now you can see 6 are in the higher energy state and 5 are in the lower energy state. Now again, if we repeat the same process, a time will come that all the nuclei they have reached or they have gone into the higher energy level. And this what could happen is there will be a what we can say, the NMR spectra will no longer be shown by this particular molecule. So in order that your molecule is giving you an NMR spectra, it is to be seen that there should be population inversion as well. That means the molecule which has gone to the higher energy state should also come down to the lower energy state so that the process is repeated and the NMR spectra is obtained. So for that, there are 2 types of relaxations. Relaxations is nothing but, ma'am, next slide. All right. So relaxation is nothing but the involvement of a known radiative transitions by which your nuclear comes down to your lower ground energy state from higher energy state. All right. I'll again repeat this thing. The relaxation process involves a non-radiative transition in which your nuclear from higher energy state, it returns to the lower energy state. Now, as I already told, returning to a lower energy state is important so as to obtain the continuous spectra of NMR. So this relaxation could be done in 2 different ways. That means loss of energy by the nucleus can be taken or can take place by 2 different ways. One is spin-spin relaxation and the other is spin lattice relaxation. See, these 2 are nothing but the loss of energy by the nucleus so that it can come down to a lower energy state. Now, what happens in spin-spin relaxation? The nuclei, which is in the higher energy state, it gives its energy to the adjacent nuclei which is present near to it so that there is no radiative transitions and energy from one nucleus is transferred into energy to the second nucleus without any radiation being transmitted. This is spin-spin relaxation. And the one nucleus, the one which has given its energy to the adjacent nuclei, it comes down to the lower energy state. The spin lattice relaxation is in which your nucleus gives its energy to the molecular lattice. So there is no net loss of energy. Your energy from the nucleus goes to the molecular lattice as a whole and your nucleus comes down to the lower energy state. So this is required so as to obtain the NMR spectra on the continuous basis. Next. Now, before moving towards the instrumentation of NMR spectra, we will understand the concept of equivalent and non-equivalent protons. Equivalent protons give you a single signal. The number of signals will depend. The number of signals that you obtain in an NMR spectra. The earlier slides, if you have seen, I had shown as NMR spectra in which lines were given. So those lines are nothing but signals in the NMR spectra. So the number of signals in the NMR spectra will depend upon the number of equivalent protons present, equivalent or non-equivalent protons present in the molecule. Now here, I've given you examples. So what is a magnetically equivalent proton? The magnetically equivalent proton is one whose chemical environment is same. In the very first picture, if you see, we have seen, I have shown the molecule of acetone. Here I'm talking about H1 NMR. That is, and we are talking about the nucleus of hydrogen, proton. Okay. Now there are 6 protons, CH3, CH3. So you have 3 plus 3, 6 protons. All these 6 protons have similar chemical environment. That means they are attached to a carbonyl carbon. That means first they are attached to the single carbon with the carbon which is attached to a carbonyl carbon. So ultimately what I want to say is that all these 6 protons, they have similar chemical environment and so they are magnetically equivalent as well. So you will get only one signal for acetone. For all the 6 protons that we have, we are going to get only one signal. Similarly for cyclohexane. In cyclohexane, we have 8 protons. But all the 8 protons are similar in its chemical as well as magnetic environment. So they are all equivalent protons. So we have a set of 8 equivalent protons. So they will again give you only one signal. In the next, if we can see, there is an example of CH3OH, methanol. Here, we have two different types of protons. Why they are different? Because their chemical environment is different, and in turn, their magnetic environment is different. Here, if you could see CH3, the protons in CH3, they are attached to a carbon, which is in turn attached to oxygen. So their chemical environment changes. Whereas if you see the proton attached, the proton which is marked as A, if you see that, it is directly attached to an electronegative atom, which is oxygen. Here, the three protons are directly attached to carbon. Here, the proton is attached to an electronegative atom, that is oxygen. So they have a different chemical environment and hence a different magnetic environment. And so we will get two different signals. One signal will be for three protons of CH3 and the other signal will be for one single proton of OH. Similarly, for the next example, that is CH3, here we have three sets of different protons. Why they are different? If we start with A, CH2Cl, in this particular, in these two protons, they are attached to a carbon, which is in turn directly attached to chlorine, the halogen chlorine. If we see the second set of protons, that is B, here these protons that are attached to a carbon, which is in turn attached to two other carbon atoms. So the environment for these hydrogens has changed. These protons' environment has changed. And if we see the third set of proton, these protons are attached to a carbon atom, which is attached with only one single carbon atom in turn. So the chemical environment of this CH3 with the protons B, that is CH2, and protons A, that is CH2 Cl wala protons, these three have a different chemical environment and so they behave in a different magnetic environment and give you different signals. So we get three different signals for this particular molecule. One will be for equivalent 3 hydrogen protons of CH3. One will be for two equivalent hydrogen protons of CH2, the middle one. And the third will be one signal for two protons, whose carbon is directly attached to a halogen atom. So this number of signals is determined by the number of equivalent protons present in the molecules. And what are equivalent protons? Equivalent protons are nothing but the protons which have similar or same magnetic environment or chemical environment. I've written a statement that magnetically equivalent protons are generally chemically equivalent protons. But the reverse of this is not always true. It is not necessary that chemically equivalent protons will always be magnetically equivalent protons. But the reverse, that is magnetically equivalent protons, they are always chemically equivalent. Next. Now we see the instrumentation of NMR spectrophotometer. See, this is NMR spectrophotometer. This is a very simple representation of the instrumentation of NMR. The components are simple. There is a radio frequency generator which generates the radio frequency waves. Next is a glass sample holder which is placed in a strong magnetic field. That means external magnetic field is given by the poles of a magnet. This in turn is connected to a detector and an amplifier, which gets connected to the display. It could be a CRO or a CRT display. So this is a simple representation of the instrumentation of NMR spectrophotometer. Now, what happens is your sample, which is to be determined or whose NMR spectra is to be taken, is placed in a glass sample holder, which is placed in an external magnetic field, and the radio frequency generator generates the radio frequency waves, and they are passed to this particular sample by the coiling of the wires. This coiling, green color shows the coiling of wires, which is which is there close to the sample holder. From here, see now, as we have already seen, NMR is nothing but the interaction of the external magnetic field with the it is the interaction of the magnetic field of the radiations that we are giving with the magnetic component of the nuclei in presence of an external magnetic field. Now we have all the three things. We have our sample, we have external magnetic field, we have our radio frequency source. Now, if you want to record the spectra of any particular molecule or any sample, you can do it in two different ways. Either you can keep the radio frequency constant and you can vary the magnitude or the strength of the applied magnetic field, or you can keep the magnetic field constant and vary the radio frequency waves that or the radio frequency energy that you are giving to your sample. But in experimentally or practically doing all these instrumentation or the experiments or the finding out the spectra, what is done is the radio frequency is kept constant and variation is done, or the different variated uh, energy of the magnetic field or the applied magnetic field that we're giving, the external magnetic field that we're giving, that is varied. That means you can change, you can keep the variable as your applied magnetic field, and the constant which is kept is your radio frequency. Whatever is the wavelength of radio frequency that you're giving to your sample, that is kept constant. And in varying applied magnetic field, at what field what strength your nucleus is resonating, those peaks are shown in your NMR spectra. Whatever is the strength of the magnetic field at which your nucleus spin flips to the higher energy state, that particular point will be given as the line or the spectra in the NMR spectrum. Next. So this is a example, or you can say the spectrum of H1 NMR spectrum of ethanol. Now here there are two different spectrum. One, the first that you see is a spectrum of ethanol which was taken in 1951 in a 30 megahertz NMR spectrophotometer. The same molecule spectrum is, the second spectrum is for the same molecule, and this spectrum is taken in a 700 megahertz NMR spectrophotometer. So this is the latest one that we are seeing. So see the difference in the spectra that we have obtained of the same molecule. Ma'am, please next. All right, so this is the very first, or you can say one of the oldest NMR spectrometer, which is a 40 megahertz NMR spectrometer. So this was the starting. It was in 1960. So this was the earliest NMR spectrometer used for the determination or the elucidation of structure of the molecules, organic molecules. Next. So it started evolving, and this is the picture or the spectrum of NMR that you are getting in 1964. So this was the way in which, this is again for 60 megahertz NMR spectrophotometer. So in those times, this was the way in which NMR spectra was deduced by the scientists. Next. So as the technology has progressed, now again in 1980, so this is the spectrogram, that NMR spectra that you get from a 60 megahertz NMR spectrophotometer, which was what you can say technologically modified in 1980s. And next. And this is the person who was given the Nobel Prize in Chemistry in 1991 for his contribution in the development of the methodology of high resolutions. The very first spectra of ethanol that I showed you, one that was at 30 megahertz and the other that was at 700 megahertz. The one which was at 30 megahertz is a low resolution spectra, and the one that you have seen 700 megahertz, in which all the splitting is shown of each and every signal, that is the high resolution spectra. And this man gets the credit for the high resolution NMR spectroscopy, Richard Ernest, and he was given the Nobel Prize in 1991 in chemistry. Next. So this is the state of art. So today's, so from where have we come? From the 30 megahertz NMR spectrometer, we have now come to 900 megahertz spectrometer with a very good high resolution, and it becomes very easy to deduce or elucidate the structures of organic molecules with the help of this technology. Ma'am, next. So these are the few more contributions towards the NMR, what I could say, NMR field, I would say. So this is the Nobel Prize in 2002 given to Kurtz, the scientist Kurtz, for his development in the NMR spectroscopy for determining three-dimensional structure for biologically macromolecular solutions. So now it is also possible to have a three-dimensional structure of huge macromolecules which exist in nature with the help of NMR spectroscopy. Next. Again, we have one more Nobel Prize in 2003. This was given in medicine to these two scientists, Paul Lauterbur and Sir Manfield. And this was given to their discoveries concerning the magnetic resonance imaging, that MRI images that we see. So these are the two people who have contributed a lot towards the MRI, that is the magnetic resonance imaging in the field of medicine. Next. So this is all possible with the developments in the NMR spectroscopy. Now we come down to a very important topic, or the very important term in NMR, that is the chemical shift. So what basically is chemical shift? We have seen the spectrum in which we have seen the signals of various nuclei that are being shown, and the position of these signals. So where you obtain that particular signal, it will give you an idea, or it will help you to understand what is the nature of the proton. If we're talking about the H1 NMR, that means we're talking about the hydrogen nucleus. So it will give you, or it will help us to understand or to know us about the nature of the proton, whether it is aromatic, whether it is aliphatic, whether it is surrounded by electronegative atoms, or whether it is surrounded by or having a group which is electron releasing. So this is all concluded by the position of the signal in the NMR spectrum. So in the electronic environment will basically tell, see, what all your molecule or your nucleus, for example, if we take the H1 NMR only, so what is the electronic environment around the nucleus of hydrogen, that will show us its absorbance in the NMR spectrum, or that will give you a corresponding signal in the NMR spectrum. So the shift in the positions of the NMR as compared to the standard, which arise due to shielding and deshielding of the protons, is called as the chemical shift. Now this you will understand in the coming few slides, what is shielding and what is deshielding and what actually is chemical shift. Now please, next slide. All right, now here we are seeing a nucleus. The very first portion of this particular image, it shows that the electron density around the nucleus is very less. As I already said, the electronic environment, that means the nucleus, how it is surrounded by the electrons, will decide what type of shift will happen to the signal of the particular nucleus. In the very first portion, as I said, the nucleus is surrounded with very low electron density. That means if we place this particular nucleus in an external magnetic field, it will feel the stronger magnetic field which is applied to it. The strength that this particular nucleus will feel is more. Now, if you see the second part of the image, here the electron density near the nucleus is more. What happens? Electron itself is spinning, it is also revolving. So what it does is, it also induces its own magnetic field. The magnetic field induced by the revolving electron is called as the secondary magnetic field, or the induced magnetic field of the electron. And this induced magnetic field of the electron is basically opposing the applied external magnetic field. So if the electron density around the nucleus is more, you need to give a larger amount of energy, external magnetic energy, for the nucleus to get into resonance. So if the electron density increases, the amount of energy required for the resonance of the nucleus also increases. Ma'am, next slide. Now here, as I said, shielding. Shielding means to protect. If the electron density near the nucleus is more, those those electrons will induce their own magnetic field, and they will oppose the external magnetic field, thereby shielding the nucleus, so as we'll have to apply a larger amount of energy for the nucleus to resonate. So this means the electrons, they have shielded your nuclei. And in such cases, as already said, amount of energy will be required, and we will say that this type of signal or this type of proton will show an upfield shift in its signal. For example, here in this very first NMR spectra you see, the proton should be showing a signal where it is written proton. That is the standard value at which your proton should be showing a signal. But because of the high electron density, because of the number of more electrons present in its vicinity, it will require more amount of energy and it will shift upfield. So this is called as shifting upfield. Whereas if you see the second spectra, in which the CH3Cl we are taking and CH4 we are comparing. One is standard CH4. The signal should be obtained for the nuclei of hydrogen in this particular region where it is written CH4. Now, if you see CH3Cl, because of the presence of Cl, what does Cl do? Cl is an electron withdrawing group. So it will take away the electrons away from the hydrogens. That means your hydrogens are being de-shielded. उनके पास कोई shielding नहीं रहेगा, कोई बचाव नहीं रहेगा. So the electron density near your protons will decrease, and so your protons will require less electric or low energy of magnetic field so as to get resonate. So your signal will shift downfield. So if it is shielding, your proton or your nucleus is shielded by the neighboring electrons, your signal shifts upfield. And if your proton is de-shielded, that means the electron density in the protons around the proton is less, it becomes de-shielded and shows signal downfield. So adding electron increases the shielding, and removing electron causes de-shielding. De-shielding shifts the signal towards downfield, and shielding takes the signal upwards in the upfield. And this changes, this shifting of the your signal from the reference or from the standard to the actual that you get because of the presence of protons is called as the chemical shift. The shift in the signal is called as the chemical shift. Ma'am, next. So electronegativity and chemical shift. We have already seen an example CH3Cl in the last slide. As there is a presence of Cl, it is an electronegative atom. It takes away the electrons from the vicinity of the protons, and so your proton becomes de-shielded and the signal shifts downfield. So similar has been indicated in this particular slide as well. So as there is the presence of an electronegative atom, it will reduce the electron density near your nucleus and your signal will shift downfields. Ma'am, next. All right, so these are the few regions in which so this slide gives you the regions of NMR spectrum, which type of proton will be seen in which area of or which type of chemical shift that particular proton will give. Ma'am, next. All right, now what is the spectral or structural information that we get from the NMR spectrum? The very first is the position of signal. As already said, the position of the signal will indicate the hydrogen, what is the type of hydrogen in the molecule. For example, if it is OH, if we are talking about OH, hydroxyl group, so this hydrogen is attached to an electronegative atom. So position of this signal will be downfields because it is attached to a electronegative atom. So the position of the signal will tell us the type of hydrogen, which type of hydrogen is present in the molecule. Then the number of signals. We have already seen equivalent protons, they give same, if we have one set of equivalent proton, we'll get one signal. If we have two sets of equivalent protons, we'll get two signals. So the number of signals will indicate the number of equivalent protons or the number of different types of hydrogen protons which are present in the molecule. Next is the intensity of the signal. So intensity of signal basically tells us about the relative amount of, or the how many hydrogens of similar type or similar kind are present in the molecule. That will be given by the intensity of the signal. And the fourth important thing that we get, information that we get, is by the spin-spin splitting of the signals. So as I already told earlier, the the NMR spectra that we used to get, they were low resolution spectra, and now because of the technological advances, we are getting very high resolution spectra in which we can see one single signal splitting into the different signals. That splitting, we'll see what are the reasons of splitting and how it happens. So spin-spin splitting, it also gives us the information about the neighboring environment of the proton or the nuclei which is under test. What type of other nuclei or other protons are present in the vicinity of the proton that is under test. And these are the scales which are used in NMR spectra. So one is a delta scale and the other is a tau scale. So they are completely opposite. That means that basically used, both of these are common, but the spectra that you basically get is on the delta scale. So if it is delta 0, that means it is tau 10. So it is reverse. And we have seen in 0, there is a TMS signal, that is tetramethylsilane. Tetramethylsilane is used as a standard for the NMR spectrum. So whatever spectra that you are deducing or you are taking for any molecule, TMS is used as a standard. Why it is used, we'll see in the next slides. So these are the two scales in which you will find your spectra. Next one. Now here, we'll see ki if a molecule is given to you, how different types of nuclei are present and how we can deduce the spectrum of the molecule. Now here we are taking an example of 2,2-dimethyl N-propanol. Now here, the very first thing that we should do after looking into the molecule is to find out the number of equivalent protons. So there are three different sets. They are shown with three different colors. So there are three different sets of protons, three different sets of equivalent protons, I would say. The 9 protons shown in pink, they are equivalent. They have similar chemical as well as magnetic environment. CH2, the proton shown in blue, has a different chemical environment than the pink. And the OH proton has a totally different chemical environment, and hence we will get three different signals for this particular molecule. 9, one signal or a singlet, you can say, for 9 equivalent protons, one singlet for the OH proton, and one for the 2 equivalent protons of CH2, methylene hydrogens. Next. Now we come to spin-spin coupling. Now what happens is, when two non-equivalent protons, in the previous example, we have seen there are three different sets of protons. Yeah. So what happens is, if non-equivalent hydrogen atoms, they are not very far, they are not far separated, what happens is, they interact, their spin interacts with, or you can say their magnetic moment interacts with each other. So what happens is, because of that, a single singlet means a single signal, that is split into n number of signals depending upon the type of neighboring proton which is present. So instead of a single peak, that is a single singlet, you get more complex patterns. You can get a doublet, you can get a triplet, quadret, pentet, or simply we can say multiplets we get. So these are, or the spin-spin coupling is because of the number and kind of hydrogens which are directly adjacent to the absorbing nuclei. So these will also give us an idea about the nature or the neighboring nature of the neighboring proton which is present for the proton neighboring atom or the nucleus which is present to the one which we are studying. Now, please next. Now here we can see the H1 spin-spin splitting. Now here we have taken an example, BrCH2 CHBr. So here we have two sets of protons. Both are attached to a electronegative atom. The only difference is the very first one, CHBr2. Here the hydrogen of CH is attached to two atoms of electronegative, having more electronegativity, and CH2 protons are attached to one electronegative atom. So the CH, the proton of CH will be more d-shielded because it is attached to two electronegative atoms, whereas the protons of CH2, they will be less d-shielded compared to CH protons. So they will be showing signal upfield. Now, simplest way to understand when you will get a splitting pattern is by seeing three bonds. If you are having a neighboring hydrogen atom which is not far away than three bonds, then that particular nuclei will have an interaction with the nuclei under test. Now here, for example, the CH, if we see the signal of CH, how many nuclei we have adjacent to it? We have two different nuclei, that is H2, two protons, H2 protons. So the splitting is n plus 1, where n represents the number of neighboring equivalent protons. Okay, so here we have two equivalent protons. So n becomes 2 plus 1. That means number of splitting of that particular signal will be into 3. It will be splitted into a triplet. So the signal of CH, it is downfield because it is attached to two electronegative atoms. Second point, it is attached to two protons, two equivalent protons, which are interacting with this particular proton, that is CH proton. So the signal of CH, which we think that should have been a singlet, but it will not be a singlet because it is interacting with the neighboring 2H protons. So the splitting will take, and the splitting will be done by in a formula, as we can say, in a ratio as such, n plus 1, where n represents the number of equivalent protons. So your CH has splitted into three signals, whereas your CH2, the protons of CH2, they are comparatively upfield and they have only one neighboring proton which is interacting with them. So n plus 1, that is 1 plus 1, that is 2. So the signal of CH2 protons is splitted into a doublet. It is not a single singlet or a single peak that we're getting. It is getting splitted into two. That means it is getting split into a doublet because of the presence of neighboring CH CH nuclei which is present there. So this is the spin-spin splitting. This is because of the neighboring nuclei which interact with the nuclei which we are considering for the NMR spectra. And next. Right. So solvents which are used for the NMR spectroscopy. So basically, the very first condition that should be satisfied by the solvent is that it should not have its own NMR spectra. Because if that happens, then it will have, I won't say it will pose a very big problem, but then yes, it will complicate the things a little bit. So solvents that basically are used for the NMR spectroscopy are CCl4, that is carbon tetrachloride, carbon disulfide, and CdCl3, that is deuteriated chloroform, CD. So instead of hydrogen CHCl3, it is CD, deuteriated. Deuterium is used instead of hydrogen. So these are the very common solvents which are used. Apart from these, there are also again very solvents. One example, very common example is dimethyl sulfoxide, DMSO. But the only thing is that DMSO is in itself NMR active, so it gives its own peak. So we have to take care that a standard should be run along with the sample so as to deduce that which peak is for DMSO, so that the remaining peaks could be considered for the sample. And next. So what is the standard that we use? As I've already told, TMS, that is tetramethylsilane, is used as a standard in NMR spectroscopy. So there are very important reasons for which we are using TMS as a standard. The very first is that it is very unreactive. That means it does not react with the molecules in which with the which we are using for the elucidation of the structure, or the molecules which are under test. The second is TMS is symmetrical. Basically, TMS is having 4 methyl groups attached to silicon. So tetramethyl. So it has 12 number of equivalent protons, and it gives a very sharp peak of its own. And it is very extremely volatile, and so the recovery of pure sample, it allows the recovery of pure sample. And the very important reason for TMS being used as a standard is that it is highly shielded. So it gives its signal very upfield as compared to most of the organic molecules which are present. So the very first signal in the NMR spectra at zero for for delta that you get at zero is for TMS, because it is the highest shielded molecule, you can say, because it is most shielded molecule, because it is having 4 CH3. So that is why the uh, signal of TMS that you get, it is very upfield, and it is considered as 0, delta, and 10 tau for the different scales of NMR spectrum. Next. So now we come to the spectrum of simple molecules. Here we are seeing the spectrum of ethanol. So this spectrum is again showing the spin-spin splitting as well. So everything is given in different colors. So here we have 3 sets of equivalent protons, as we have already seen ethanol. So one is for CH3, the protons, CH3 protons, they are equivalent. Second is CH2 protons, this is the second set of protons, and the last set of proton is your OH proton. Now these are the signals that we are seeing. The very first signal that we are having at around 1.3, that is for the CH3, and it is a triplet. It is a triplet. Why? Because on the adjacent carbon there are 2 different protons, so n plus 1, that is 2 plus 1 3. So the signal for CH3 has been splitted into 3, that is we are getting a triplet for CH3. Next is your OH, the signal for the hydrogen that is attached to oxygen. It is again a little downfield, and it is a singlet because it is not interacting with any other neighboring nuclei. And the last signal that we are getting is for CH2. This signal, in this particular signal, this signal is split into 4 quadrate. Reason? Because neighboring adjacent nuclei, we have 3 different protons. So 3 plus, that is n plus 1. So 3 plus 1, 4. So your signal for CH2 protons is split into a quadrate. Now here the hydrogen present in along with oxygen, the hydrogen of OH, it does not interact with the nuclei, other nuclei of protons. That means the ones which CH2 protons, it does not interact. CH3 is still very far away. So while considering the splitting of CH2 protons, we are only considering the interaction of CH2 protons with the protons of CH3. Next. All right, so this is the next spectra. This is, again, we have 2 different sets of protons. One is for CH3, the other is CH. Now here, the CH proton is highly deshielded. Reason is because it is connected to 2 electronegative atoms. So the electron density in the vicinity of this particular proton is very much less. So this is deshielded, and so the signal for that particular proton we are getting downfields. Now the protons, this particular proton, if we see and we see the bonds from that, we can see that the neighboring protons are only 3 bonds away. So that means these neighboring protons will also interact with the CH. So the splitting of this particular signal will be a quadrate. Reason for being it quadrate is again the formula n plus 1, where n is 3 because we are having CH3. So 3 protons are there. So the signal for CH is split into a quadrate. Whereas if we see the signal for CH3, these are shielded. So the signal is upfields. Here again, we are seeing a signal of TMS at 0. Now we are seeing the splitting of CH3 into 2. The reason is again, they have a neighboring proton, single proton, CH proton. So N plus 1, that becomes 1 plus 1, 2. So the signal of CH3 over here has been split into 2. So we are getting, this is the high resolution spectra of this particular molecule. Next. So this is again the NMR spectra of ethyl acetate. Now here again we have shown the number of equivalent protons with different colors. So there are 3 sets of equivalent protons. One is CH3, which is directly attached to COO group. Next, CH3 is attached to CH2, and the third equivalent set is CH2 protons. So as again, if you see the CH3 protons, it is the alkyl group, it is the alkyl group, and so it will give its signal upfield. So the very first signal that you're getting around 1.3 and 1.4 is for the CH3. Now this CH3 signal is again split into what you can say, it is split into a triplet. Then the signal for CH2, it is split, it is downfield because the carbon for CH2 is directly attached to oxygen. So that particular signal, you are getting a quadrate. Reason for that being is that it is having an interaction with the neighboring 3 hydrogens of CH3. So 3 plus 1, it is shifted into a quadrate. Now, whereas for the last, that is CH3, these protons are not interacting with any other nuclei in their neighborhood. So we are getting a singlet signal for these CH3 protons shown in green color. So we are getting only singlet because there is no neighboring nuclei to interact with it, and so the signal has not split into the multiplets. Next. All right, so this is the spectra of an aromatic compound. So benzene ring, it will always take into an account that we have seen the, I showed you a slide in which there were regions given for each type of protons. So the aromatic ring protons, they generally give you signal in between 6.5 to 7.5. So the multiplet that we are seeing here in the region of 6.5 to 7, that is for the protons of the aromatic ring that is present. So this is a multiplet. Now here again we have 4 sets of protons. The one is CH3, second set is CH2, third is the OH proton, and the fourth one is the aromatic protons which are there. So the aromatic protons are the because there is the resonance in the aromatic ring, so de-shielding of your aromatic ring takes place, so you are getting the signal downfields. The very first signal that we are seeing is a triplet for CH3. Again, the reason for it being a triplet is because in the neighborhood there are 2 protons. So 2 plus 1, 3. So the signal for CH3 will be split into a triplet, and it is an alkyl group, so it comes around 1.2 to 1.3. The signal is shown at 1.2 to 1.3. The second signal which is shown is for CH2, and it is a quadrate. The reason for being it a quadrate is that it is in the vicinity of 3 equivalent hydrogens. So 3 plus 1, 4. So the signal for CH2, the protons of CH2 will be split into a quadrate. And the third signal is for OH. Again here, the proton which is attached to oxygen directly, it does not interact with the neighboring. There is no neighboring proton to interact with. So therefore, the signal that we get for the OH is a singlet. So there is no splitting of this particular signal. So these were the few what you can say spectra that we have seen. Simple spectra of very simple organic molecules. The NMR spectra could be very, very interesting to understand, and they could be sometimes complex to deduce as well. But these were the very simple molecules that you come across in regularly in chemistry. So we have seen the spectra of these simple molecules. So I guess, ma'am, the last slide. So thank you so much. Thank you for being patiently listening. And if you have any questions, you can kindly ask.
Thank you so very much, ma'am.
My pleasure, ma'am. Thank you.
Yeah, it was actually this topic is a bit cumbersome, you can say.
Yes,
Students, it will take bit time to recall and
yes.
to just ask the questions. I hope there is no question. There is no question from student side. Thank you so very much, ma'am. Indeed, very much honored to have you on this platform and
Thank you
hope
so
to
much, ma'am.
have the
Thank you for giving the
association and the
opportunity.
collaboration
Definitely,
and
ma'am.
hope to
Thank you
have
so
the
much.
same thing in future as well. Thank you so very
Yes,
much.
ma'am. Definitely, ma'am. Thank you so much, ma'am. Thank you so much.
Okay, ma'am. Thank you so much. So we have
Thank you.
from the studio. Okay, good day. Bye bye.
Yeah. Well, thank you.